Hello, my name is David Lee Jr. and this is my Lab 1 report focused on constant motion. So we're going to start with the table of contents. We're going to first introduce the experiment and the important concepts we need to understand before talking about the experiment. Then we're going to talk about the analysis of the basketball's motion, discuss the computational model I constructed based upon the analysis of the basketball's motion, then discuss observed motion versus predicted motion, and finally answer two essential questions proposed in the lab's instructions. So firstly, we need to introduce the key concepts. This lab is focused on constant motion, which means that the net force acting upon the object equals zero. This is very important to make the distinction that this does not necessarily mean no forces are acted upon the object. The net force can also equal zero if all the forces on the object equal to zero. This lab is going to prove Newton's second law, but it includes and incorporates concepts from Newton's first law. We're going to be using both the velocity update formula and the position update formula later on to better understand not just the experiment, but also construct the computational model. This diagram depicts the motion of the position, the velocity, and acceleration of an object in constant motion. It's also very important to make the distinction that in the computational model, we are making an assumption that friction, air resistance, and any other surroundings do not exert first force on the ball. So to analyze the basketball's motion, I use Tracker. Tracker is used here to plot the basketball's motion relative to time, or respective to time. As seen in the video, I chose to roll the ball from the left to the right. This means that I selected the right side to be positive. Because my ball moves alongside the x-axis to the right, the resulting position versus time graph is positive and increasing to the right. To predict the basketball's motion using the computational model, I used the starter code and updated the velocity update and position update functions to incorporate Newton's second law as shown by the equations. I also changed the mass so the program reflected the correct mass of a basketball, but because our net force is zero, mass will also be zero, so the value of mass when modeling constant motion is negligible. I also needed to change the initial position and velocity of the basketball. To obtain the correct value for position, I simply placed the coordinate axis on the first analyzed frame at 0 for x and for y. So our initial position is a nice 0 vector. To obtain the initial velocity, I again used the initial position, selected the next point of position, and used the velocity formula, which is change in position over change in time, to find the initial velocity. Because the object is moving at a constant pace, any point could have been used to obtain this velocity. Time was set equal to 0, and my video was shot in 60 frames per second, so I chose 1 over 60 as my delta t. I again used the starter code to build the model after setting the initial conditions. So here in the screenshot shows the while loop that runs the actual bulk of the code that updates the velocity and the position according to the net force. The while loop is set to end by the same amount of time elapsed in my experiment. The net force vector is set to 0, as we are observing constant motion. My experimental results differed greatly from the predicted results, especially as time progressed. While the assumptions we make in the computational model assume that friction and all other forces, such as air resistance, friction, and gravity, are not acting upon the object, in the real world, those forces are still present. In my experiment, the motion still appears to be constant, both in the video and in the graph, but has a much steeper slope than the prediction model. One of the reasons for this may be the wind blowing on the ball, or maybe even a slight slope in the driveway. There's also the element of human error. I could have made errors either in Tracker or not selected frames where the ball was moving constantly. If the axes were flipped, and here I'm answering the two essential questions in the lab instructions. If the axes were flipped, my graph would be negative in the x direction and slope downwards, but my model would still be an under-prediction of the basketball's motion regardless of the orientation of the axes. It would be very difficult for me to say how many forces were added together to sum the zero net force, as there are a multitude of forces acting on the ball, such as gravity, air resistance, and friction. If I could somehow account for these forces in the model, it would more accurately represent the motion of the basketball. However, I can also eliminate some of the forces by conducting the experiment inside, negating air resistance, on a surface that I am 100% sure has no slope. This would help make my experiment a more accurate representation of constant motion while ensuring nothing but friction and gravity will be acting upon the object, which we could account for in our model. Thank you for listening to my presentation.